Hey everyone, and welcome to this quick revision explainer on oscillations. We're going to do a crash course on all the key concepts, the big derivations, and those must-know formulas for your exams. All right, let's jump right in.
So, to get things started, let's kick off with a question. I want you to picture a few things: a pendulum swinging back and forth, a guitar string vibrating to make a note, and even the springs in your car bouncing after a pothole. They seem pretty different, right? But what's the one physics principle that ties them all together? Well, if you guessed that it's all about a special kind of back-and-forth motion, you're exactly right. And that brings us to the heart of this whole chapter: simple harmonic motion, or as we all know it, SHM. So let's build this up from the very basics.
Okay, first things first, we've got to nail down a really important distinction. You see, all oscillatory motion is periodic. That just means it repeats over and over. But, and this is the key part, not all periodic motion is oscillatory. Think about the Earth going around the Sun. Is it periodic? For sure, once a year. But is it moving back and forth over the same path? No. To be oscillatory, you need that classic to and fro movement. It's a subtle point, but a crucial one.
And that leads us right to the main event: linear simple harmonic motion. This is the simplest, most perfect form of oscillation you can get. There are two non-negotiable rules for SHM. Rule 1, there's always a force pulling the object back to the center or its mean position. And Rule 2, the further you pull the object away, the stronger that pull back to the center gets. That's it. All right, pencils ready? This is where we get into the math behind the magic. And look, don't just memorize these equations. If you can understand where they come from, you'll be able to solve pretty much any problem they throw at you. So let's walk through it.
It all starts with this thing called the restoring force. This is the force that's always trying to get things back to normal, back to equilibrium. We describe it with Hooke's law, F equals negative kx. Now k is just a constant for the spring or whatever is oscillating. But that little minus sign, super important. It tells us the force is always pulling in the opposite direction of the displacement. You pull right, it pulls left.
Next up, we bring in an old friend, the one and only Newton's second law. You know this one by heart, F equals ma. It's the universal rule for how force, mass, and acceleration relate to each other. And now for the cool part. We've got two different ways to describe the force, right? So, let's just set them equal to each other. ma equals negative kx. We just rewrite acceleration in its calculus form as the second derivative of position, and we get this. This equation, right here, is the mathematical DNA of simple harmonic motion. It's the master code.
Now that k/m term looks a little clunky, so physicists like to tidy things up. We just group those constants together and call them omega squared, where omega is the angular frequency. And this is the final clean version of the equation you need to burn into your brain.
Now, good news, for most of your exams, you probably won't have to solve that big equation from scratch, but you absolutely have to know what the solutions look like. And here they are. These three formulas are your toolkit. They tell you the object's position, its velocity, and its acceleration at any given moment.
Man, I love this table. It's like the entire story of SHM in one little box. And you can really see the trade-off, can't you? Right in the middle, at the mean position, the object is moving at its absolute fastest, but there's no acceleration. Then, at the very ends of the swing, it stops for a split second, zero velocity. But that's where the force pulling it back is strongest, so acceleration is at its max. Get this relationship, and you've got SHM down.
Okay, so we've talked about how these things move, but what about the why? What's powering this endless back and forth? Let's talk about energy. Where is it, and where does it go?
So the total energy in the system is constantly swapping between two forms. You've got kinetic energy, that's your moving energy, which is at its peak right in the middle where it's going fastest. And then you've got potential energy, that's stored up energy, which is maxed out at the ends, right when the object is about to turn around.
But here's the really beautiful part. If you add the kinetic and the potential energy together at any point in the cycle, guess what? The total is always the same. The total energy is conserved. It's just passing the energy back and forth between motion and storage, like a perfect closed system. It's so elegant.
Okay, we've got all this awesome theory under our belts. Now let's see how it works in the real world with the most classic example there is, this simple pendulum. This is a huge topic for exams, so let's nail it.
This derivation shows up all the time, so let's just break it down. We start by figuring out the restoring force. It's just a little piece of gravity. Now the secret weapon here is in step 2, the small angle approximation. It's a clever math shortcut that lets us simplify the whole thing. From there, we can find acceleration, compare it to our standard SHM equation, and bam, we can solve for the period t.
And after all that work, we get this absolute gem of a formula. The period t is 2 pi times the square root of the length L over gravity g. I can pretty much guarantee you're going to see questions that use this, so star it, highlight it, whatever you need to do to remember it.
What's so great about this formula is that it tells us everything we need to know. It gives us 4 simple laws. The period depends on the pendulum's length and on gravity. But look what's not in the formula: the mass of the bob. And as long as the swings are small, it doesn't matter how far back you pull it. Kind of crazy, right? It just doesn't affect the timing.
Whew, okay, that was a lot. So before we wrap this up, let's do a super quick, rapid-fire review of the formulas you absolutely have to know. This is your final cheat sheet. You ready?
First up, displacement. This is your go-to for finding the position of the particle at any specific time, t. Next, velocity. This one is perfect for when you know where the particle is and you want to know how fast it's going.
Then we have acceleration. So simple, so elegant. It just tells you the acceleration is proportional to the displacement, but in the opposite direction. And finally, total energy. Remember, it's always constant, and it only depends on that k value and the square of the amplitude. So simple, but so powerful. So, we've absolutely nailed the basics of simple oscillations today, but I want to leave you with one last thought to chew on. What happens if you start pushing a swing, but you push it at just the right moment in its cycle every single time? The swing goes higher and higher and higher. That phenomenon has a name. It's called resonance, and it's powerful enough to shatter a wine glass with sound, or in some famous cases, even bring down entire bridges. But that is a story for our next explainer.